Atomic spectroscopy. In case of atomic spectroscopy, the light interacts with matter and the matter exists in the atomic form. Atomic spectroscopy includes a number of analytical techniques used to determine the elemental composition of a sample. A sample may be in gaseous form or in liquid form or in solid form. By observing its electromagnetic spectrum or mass spectrum, with the help of observing electromagnetic spectrum or mass spectrum, we can find the elemental composition of a sample, and we can also find the quantity of a sample. Atomic spectroscopy include very sensitive techniques because with the help of atomic spectroscopy, we can quantify the amount of unknown element up to 1 million part or up to 1 billion part. There are different types of atomic spectroscopy like atomic absorption spectroscopy, atomic emission spectroscopy, atomic fluorescence spectroscopy, X-ray fluorescence spectroscopy, atomic mass spectrometry. Why atoms absorb radiation, or in other words, interpretation of atomic spectra. Here you see, this is the nucleus of atom, and around the nucleus, these are the shell or the orbitals where the electron exists, and this is the K, L, and M shells. Okay, so here you see, so there are different energy levels. They also called orbitals. Okay, so the shell which is close to the nucleus, which is of low energy level, and there is another one. This is a little away. This is the L shell, so its energy is little more as compared to K shell, and after that KLM, and this is having more energy. Okay, so here you see in between different shell there is the energy gap. Okay, so in an atom there are a number of shells and of subshell where electron can be found. In the energy level of each shell and subshell are different and quantized. Here you see this is having one type of energy, this shell is having another type of energy, because here you see they have the energy difference. The electrons in the shell closest to the nucleus has the lowest energy. The higher shell number is, the higher energy it is. The exact energy level of each shell and subshell varies with the substance. Ground state and excited state of electron. Under normal situation, an electron stays at the lowest possible shell. The electron is said to be at its ground state. Absorbing energy, an electron jump from one orbital to another one, okay, and we say that the electron is at excited state. Here you see this N1, N2, N3, these are different shells and these are the subshells. Okay, so when the electron is here, okay, and there is the energy is not absorbed by the electrons, we say the atom is in the ground state. But when the light interact here and this electron jump from this level to this level, okay, so we say that we call excitation. There is excitation of electron, and in this case we say that the atom is in the excited state, and so on. The level and the amount of energy supplied to excite electron can be measured and studied in terms of frequency and intensity of electromagnetic radiation. That we know excitation is absorption, that is a kind of absorption spectroscopy. So when an electron absorbs energy and it jumps from here to here, or this electron jump from here to here, okay, so excitation, and this is the amount of energy is absorbed. You know, light is also a type of energy. Okay, light is also having energy, and the energy of light is equal to E is equal to h mu. Okay, so when the electron absorb light, it means it absorb energy, and when it absorb energy, so it jump from low energy level to high energy level, and this kind of jumping we call excitation. And after absorption of energy, we say that the atom is in excited state. Okay, when the electron come back to its ground state, so the extra energy it emit in the form of light, okay, and that light then we call emission, and we can measure that emitted radiations. Okay, so the kind of spectroscopy in which we are measuring the emitted radiation that we call emission spectroscopy, and the kind of spectroscopy in that we are measuring the absorbed radiation, so that we call absorption spectroscopy. Here you see, in case of absorption, there is a ground state, the light radiation. Suppose there is electron at this level, at the ground state. When it absorbs energy, it jumps to the high energy level. It may be jump here or here or here. So we say the energy will be absorbed, because here you see this energy gap. Here is some energy is required, and this energy is provided by the light energy. So when the light energy interact with the matter in atomic form, so what's happening? An electron jump from the ground state to the excited state. It can jump from here to here or here or here. When an electron come back to the ground state, suppose the electron is at excited state, and when it come back to the ground state, so the extra energy it emit in the form of light. Okay, so this kind of spectroscopy we call emission. Okay, and when the de-excitation is this we call de-excitation, and here in absorption we call the excitation. This is de-excitation is the opposite of excitation, and when the de-excitation is from the singlet excited state to singlet ground state, so we call it fluorescence. In atomic absorption, atomic emission, and atomic fluorescence exploit interaction between light and the valence electron of pre-gaseous atoms. When light of a specific wavelength enters in an analytical system, outer shell electron of the corresponding atoms will be excited as energy is absorbed. Here, suppose you have the electron when the light is interacted. So what's happening? This electron will jump from here to here, and this jumping of electron from the ground state to the excited state we call excitation. As a result, the amount of light transmitted from the system to detector will be reduced. This is understood as atomic absorption spectroscopy. The delta E for the moment of valence electron in most elements meets the energy of equal to the ultraviolet or visible radiations. And this excitation, jumping of electron from here to here, this is quantized. Okay, quantized, what is mean by quantized? Means those wavelength of radiation or those wavelength of radiation will be absorbed. The energy of those wavelength of radiation is equal to the energy difference, this energy difference. So delta E is equal to h mu, and this is equal to hc by lambda. Okay, so those, what is this lambda? That is wavelength. Okay, so this wavelength means here the energy of the wavelength that is equal to the energy, this energy difference, so that will be absorbed. And here you see again, when the electron is here at the excited state, so here it stay for very short time at the excited state, and it has to come back to the ground state. So when it come back to the ground state, and this we call de-excitation. So in case of this excitation, the amount of energy which it is having at the excited state, it release in the form of light. So this we call de-excitation. In case of de-excitation, we are getting the radiation, those radiations are emitted, and this kind of spectroscopy in which we are measuring the emitted radiations, that is known as emission spectroscopy. While in case of X-rays fluorescence, what's happening? So we have the inner shell electron. What we are doing, this inner shell electron, here you see the electron, that we eject this electron. Okay, and once you eject the electron, there will be empty space. Okay, in order to fill this empty space, the valence shell electron come to this inner shell level. Okay, and here you see there is energy difference, and this extra energy it emit in the form of radiations, and those radiations then we call it X-rays. When high energy photon strikes to a massive particle, it can excite an inner shell electron of the atom. The forming inner orbital vacancy can be filled with an outer shell electron. The transition is created by an emission of X-rays photon. This process is called X-rays fluorescence. Once again, here there is inertial electron. This inertial electron is ejected. When this electron is ejected, there will be the empty vacancy. In order to fill this empty vacancy, so the outer shell electron uh, come here to fill this vacancy. And here you see when the electron is here and here, because there is the energy gap between two shell, two energy levels. Okay, so this extra energy it emits in the form of X-rays. And this in X-ray spectroscopy, what we are doing, we are measuring the X-rays emitted radiation. The high temperature inductively coupled plasma has been successfully used as an effective ion source for mass spectroscopy or emission spectroscopy. The type of method of inductively coupled plasma mass spectroscopy, ICP-MS or ICP-OES, are routinely used for measurement of trace element in clinical and biological sample. Here you see this is the inductively coupled plasma. You know plasma, later on I will explain what is mean by ICP and what is mean by plasma. So here you see this is the light source, and here you see this is the atomizer, and here the atomizer is in the form of plasma, and here this is wavelength selector, and here you see the detector and signal processor. What a spectrum tells, here in this diagram, here you see the spectrum. The spectrum is a curve. On one side we are taking either intensity, emission intensity. On the other side we are taking the wavelength or wave number. Here you see we are taking the energy or emission intensity and wave number. Sometimes we are taking here the absorption, uh, the absorption intensity. Instrumentation that we are using in atomic spectroscopy. In atomic spectroscopy, we are using light source, nebulizer, atomizer, monochromator, and detector. Here you see this is the light source, here the atomizer, monochromator, detector, and the readout device. Once again, here you see this is the atomizer, this is the flame, and here this is the light source, monochromator, detector, amplifier, and readout device. Atomic or line light sources. Uh, in atomic spectroscopy, we are using three types of light sources. One is low pressure mercury arc lamps. The second one is hollow cathode lamps. And the third one is the lasers. There are three types of atomic or line light sources used in atomic spectroscopy: low pressure mercury arc lamp, hollow cathode lamp, and lasers. Line source can be used in the UV visible region. Low pressure mercury arc lamps are very common sources for use in liquid chromatography detectors. The dominant line emitted by these sources is at 253.7 nanometer. Hollow cathode lamps are also common line source used specifically for atomic absorption spectroscopy. Lasers have also been used in molecular and atomic spectroscopy, both for single wavelength and for scanning application. Here you see this is the low pressure mercury arc lamp, are a very common source for use in liquid chromatography detectors. Mercury vapor lamps are probably the most common and emit intense light at 253.7 nanometer. Because of the limited emission spectra of the lamp, wavelengths are not adjustable. Because of the intensity of the radiation, fixed wavelength detectors can be up to 20 times more sensitive than variable wavelength detectors. Here you see this is the mercury arc lamp. Here you see the molybdenum foil here, electrode system here, tungsten electrode. Here this is the tungsten electrode, this is the quartz envelope, so on. Hollow cathode lamps. These are the most popular lamps that we are using in atomic spectroscopy. Here you see the In this diagram, you see the hollow cathode lamp. Here you see this is a glass tube. Inside the glass tube, here you see here is the hollow cathode, and here this is the anode. Okay. An illustration of the hollow cathode lamp is given in a figure. In this system, the metal of interest is used as the material from which the cathode is made. Here you see this is the cathode part. So usually the cathode is made of the material which we are going to analyze. So we can say that the material of interest. So the cathode material will be the material of interest that we are going to analyze or that we are going to quantify. The light source is filled with an inert gas such as neon or argon. Here this tube is filled with the inert gases. Here you see neon or argon gases, which is ionized by the anode. Here you see on this black shape, black color, here you see this is the anode. The positively charged argon or neon ions are then attracted by negatively charged cathode. When this, here you see this uh, inert gases are ionized with the help of anode, and when they are ionized, so they are attracted toward the cathode with the potential difference. Because of the potential difference, on arrival at the cathode, the positive ions strike the surface of the cathode. When they strike with the surface of the cathode, if it has sufficient energy, it causes atom of the cathode to be ejected. This process in which the atoms of cathodes are ejected we call sputtering. The sputtered atoms emits photon at characteristic atoms lines as the metal returns to the ground state. The emitted lines are generally very narrow and in bandwidth. So when the excited metal, because the metal is excited, this sputtered metal, it is excited, and when it comes to the ground state, so the extra energy it emits in the form of light, and that light we call line source of light. Here you see this is the inert gas ion. When it strikes with the cathode surface, it's sputtering the metals. And when the metals, here you see this is excited, and when it's come to the ground state, so the extra energy it emits in the form of light, and this light is known as line source light. Lasers. Laser is a special type of light source or light generator. The word laser represents light amplification by stimulated emission of radiation. Here you see this is the laser generator source, and here the radiation we are getting here, these are called laser. Light amplification by stimulated emission of radiation. Characteristic of laser radiations: monochromatic, single wavelength. All the radiation that we are getting from the laser source, those are monochromatic. They are coherent. Here you see they are in phase. What is meant by in phase? Here you see this is the trough and the crest. They are in same phase. Okay, so all the radiation, those are generated by the laser source. They are coherent, directional, narrow, cone of divergence. They are very directional in one specific direction. They are always directing in a specific direction. The other light source, just like an incandescent lamp source, here you see the radiations are polychromatic radiations, many colors, many different colors, just like the tungsten bulb. Okay, they are not coherent, and they are not unidirectional. They are multidirectional. In this direction, in this direction, in this direction, and so on. Atomizers. In atomic spectroscopy, the elements to be analyzed need to be in atomic state. Atomization is separation of particles into individual molecules and breaking molecules into atoms. This is done by exposing the analyte to a high temperature source, and that is known as atomizer. Types of atomizer. In atomic spectroscopy, we are using different types of atomizer like flame atomizer, electrothermal atomizer, ICP inductively coupled plasma atomizers, and here you see the hydride generation atomizer. Flame atomization. The flame atomization system used in atomic spectroscopy convert the analyte solution into free atoms in the optical path via successive stages. What are those successive stages? Here you see this is the diagram. It shows the flame. Okay, and the temperature of the flame usually this is around 1500 to 1700 degrees Celsius. Okay, and there are different stages. Here you see the first stage is the nebulization, the second one is desolvation, mixing, desolvation, and after that is vaporization, and after that is the atomization. The primary aim of the sample introduction system is to generate an aerosol of sample in the fuel mixture. This requires the production of an aerosol with a sufficient number of small droplets and to introduce a portion of the sample in the flame without experiencing difficulties such as nebulizer or burner blockage. The usual means of sample introduction is to use a nebulizer to create the aerosol and a spray chamber to filter larger droplet from the aerosol. So here you see nebulizers suck up liquid sample at a controlled rate. The first stage here, this is nebulization. The nebulizer suck the solution here and that in the form of the droplets. Create a fine aerosol spray for introduction into the flame. Mix the aerosol and fuel and oxidant thoroughly for introduction into the flame. Here you see there is the mixing, the fuel and the droplets, and here you see it come here. After that there is the vaporization, desolvation, remove the solvent, and then vaporize the sample. After vaporization there is the atomization, because it has to break the molecule and convert it into atomic form, okay, free atoms. So that is called atomization. Okay. uh, Disadvantages of flame atomization: only 5 to 15% of the nebulized sample reaches the flame. A minimum sample volume 0.5 to 1 ml is needed to give a reliable reading. Samples which are viscous require dilution with a solvent. The other kind of atomizer, that is electrothermal atomization. Here you see this is the graphite furnace atomizer. Here you see this is a graphite tube, one tube. This is, here you see the tube, and here you see this is the window through which we can insert, or we can introduce the sample here. Okay, and here you see the electrical connector here, insulator, and here you see this is the light beam passed from the sample through this here. So with graphite furnace atomization, the frame is replaced by an electrically heated graphite tube in an argon to vaporize the sample. So here we are not using flame, we are using the heating element around the graphite tube. So through the heating element here you see that is around the graphite tube. So we heat up the sample through the electricity, not with the flame. Okay, and once we heat up the sample, so there is the atomization, and when it convert into the atomic form, so then we interact the light radiation when the sample convert into atomic form. A small volume of sample, usually between 1 to 70 microliter, but typically around 20 microliter, is dispensed directly into pyrolytically coated graphite tube. Graphite coated tube which can then be heated to vaporize and atomize the sample. The graphite tubes are heated using a high current power supply. Advantages of graphite furnace techniques: small sample size or solid sample can be analyzed with the help of graphite furnace tube. Very little or no sample preparation is needed. Sensitivity is enhanced. Direct analysis of solid sample we can do with the help of graphite furnace. Disadvantages of graphite furnace technique: analyte may be lost at the etching stage. Sometimes the analyte converts into ashes and it's going to lose. The sample may not be completely atomized. Sometimes the sample is not going to completely atomize. The precision is poor than flame method. Analytical range is relatively low. Vapor generation or hydride generation system. Here you can see the hydride generation system. It consists of pump, reactor, separator. The first part here you see, suck up the liquid sample at a control rate. Then it comes here to the second stage, mix liquid sample with the sodium borohydride and HCl. Because in hydrogenation, what's happening, the sample is going to mix with the sodium borohydride and acid, and after that create a volatile hydride of the analyte, and after that flow the gaseous hydride into the optical cell. So when the analyte react with the sodium borohydride, so what's happening, create a volatile hydride of the analyte metallite from the reaction. So this reaction is producing a metallite hydride, means the analyte convert into the atomic form, okay, and from that atomic form flow the gaseous hydride into the optical cell, and through that we interact the light. Vapor generation detection limit are usually in the subparts per billion, means they are very sensitive. The cold vapor technique is the most sensitive method available for the detection of ultra trace level of mercury, and usually it is used for the arsenic, selenium, antimony and mercury determination in environmental sample. The hydride generation method, this is very sensitive technique. With the help of that we can go to the ultra trace level to quantify. Inductively coupled plasma source. What is plasma? A plasma is a hot, partially ionized gas. It contains relatively high concentration of ions and electrons. So you know what is plasma? Plasma is a mixture of ions and electrons. Argon ions, once formed in a plasma, are capable of absorbing sufficient power from an external source to maintain the temperature at a level at which further ionization sustains the plasma indefinitely. The plasma temperature is about 10,000 Kelvin. In contrast to a flame, it is necessary to supply an external energy in the form of electrical field in order to ionize the gas and to sustain the plasma, which in turn will transmit part of the energy to the sample, atomize, ionize and excite it. ICP is obtained when a high frequency field is applied through a coil. Here you see this is the plasma, and here you see this is the coil, okay, and here you see we are getting the plasma. Plasma is actually a mixture of the ion and electron. The gas that is used to generate the plasma is argon. Like any noble gas, argon is monoatomic element with a high ionization energy, 15.7 electron volt, and is chemically inert. Here you see again, because we are using as an atomizer, so here from the solution there is the From here the source of the droplets, that vaporization, after that atomization, and there is ionization, and after ionization there will be the excitation. Wavelength selector or monochromators. This is a very important part in an atomic spectrometer. It is used to separate out all of the thousands of lines. A monochromator is used to select the specific wavelength of light which is absorbed by the sample and to exclude other wavelengths. Those are not needed. The selection of the specific light allows the determination of the selected element in the presence of other. We are using the polychromatic light which containing many wavelengths. Monochromatic means which containing only one specific wavelength. So the device, with the help of that, we can separate the different wavelength from each others. That is known as monochromator. Here you see the grating. We have different types of monochromator. One is the grating, prism, filters. These are the different types of monochromator we are using. So here, this is the part which we also call it is the wavelength selector or monochromator. With the help of that, what we can do, we can separate the different wavelength from each other, and a specific wavelength then we can target at the sample. This is a very important part in atomic spectrometer. It is used to separate out all of the thousands of lines. A monochromator is used to select the specific light which is absorbed by the sample, and so on. Our monochromator consists of entrance slit. Here this is the light source which emits the polychromatic light, and here this is the entrance slit, and after that this is the mirror, and this mirror then here this is another mirror, and here you see this is the monochromator, this is the grating. Okay, and after striking the grating, so here the different wavelengths are separated. Here you see one wavelength, another wavelength, another wavelength, and a specific wavelength then we target upon the analyzed sample. Detector. The light selected by monochromator is directed onto a detector that is typically a photomultiplier tube whose function is to convert the light signal into an electrical signal. We also call it transducer. With the help of detector, what we do, the light signal we are converting into electrical signal. The most popular one is the photomultiplier tube. Here you see this is the photomultiplier tube. Optical signal is fulfilled by the signal. Okay, what is happening here you see this is a photocathode. Okay, and the light here strike and it emit the radiation. Okay, and here it strike with the diodes, and there are amplification of light. There is emission of 2 radiation, and it's again strike with another diode, and there is emission of 4, and it's going to amplify or it's going to multiply. Okay, and here the light signal is converted into what? Into electrical signal, means into electron, because here you see when the light strike here, ejection of 1 electron, here is ejection of 2 electron, here is ejection of 4, and so on. So this is also at the same time, in case of photomultiplier tube, the electrical signal is going to amplify, it is going to increase. So detector is that device which converts the light signal into electrical signal. Detector use a sensitive transducer that converts a signal come from light energy into electron. An ideal detector produced signal is a linear function of the electromagnetic radiation power. Phototubes and photomultiplier tubes are the most popular one. There are so many other detectors that we are using in spectroscopy. Here you see this is the detector. Here you see the diodes 1, 2, 3, 4, 5. You increase in the number of diodes, dynamics, so you are going to amplify the signal. Recorder. A transducer electrical signal is sent to a signal processor where it is displayed in the form that is more convenient to explain. The analog meter, digital meter, recorder, and computer equipped with data acquisition boards are good examples of signal processor. A signal processor is used in calibrating the detector response, amplifying the transducer signal, removing noise by filtering, or mathematically transforming the signal. In this table, you see different types of the detector: phototube, photomultiplier tube, silicon photodiode, photoconductor, photovoltaic cell, thermocouple, thermistor, pneumatic, pyroelectric. Calibration curve. A calibration curve is used to determine the unknown concentration of an element in a solution. Here you see this diagram shows a calibration curve. It's a curve between the concentration of the analyte and the absorption or emission intensity versus absorption or emission intensity. In order to make the calibration curve, we also call regression curve. What we have to do first, we need to prepare the standard solutions, and for each standard solution we need to measure the absorption, and then plotting the absorbance versus the concentrations. We are getting here a straight line. This we call regression line. And for unknown solution, what we are doing, we are measuring the absorption. Suppose we got the absorption here, and then we extrapolating here and putting a projection here, perpendicular here. So from here we can find the concentration of the unknown. So a calibration curve is used to determine the unknown concentration from an element in a solution. The instrument is calibrated using several solutions of known concentration, those we call standard solution. The absorption of each known solution is measured and then calibrated. Calibration curve of concentration versus absorbed is plotted. Sample solution is fed into the instrument and the absorption of the element in this solution is measured. The unknown concentration of the element is then calculated from the calibration curve. Application. With the help of atomic spectroscopy, we can find the presence of metals as impurity or in alloys could be done easily. Level of metals could be detected in tissue sample like aluminium in blood or copper in brain tissue. Due to wear and tear, there are different sorts of metal which are given in the lubrication oil, which could be determined for the analysis of condition of machines. Determination of elements in the agriculture and food products. Application of atomic absorption spectroscopy, water analysis, for example, for the calcium quantification, determination, magnesium, iron, silicon, aluminium, barium. Food analysis, analysis of animal feedstuff, analysis of additive in lubricant oil and greases, analysis of soil, clinical analysis like blood sample, whole blood sample, plasma serum, and so on. Comparison between atomic spectroscopy, atomic emission spectroscopy, and atomic absorption spectroscopy. The first comparison, this is here, we are measuring the emitted radiations, and here we are measuring the absorbed radiation. This is de-excitation process, and here this is excitation process. Sample preparation. Sample preparation should remove interfering component from the matrix and to adjust analyte to facilitate the actual measurement. Method for the destruction of the organic matrix by simple heating or by acid digestion have been developed and thoroughly approved. Microwave heating is used for this purposes. With the specifically designed a compatible equipment to avoid dangers of excessive pressure within the reaction flask. Although the number of samples that can be processed is not large, microwave heating digestion afford rapid digestion and low region blanks More recent development include continuous flow system for automated digestion, which has a direct link with the instrument. Atomic spectra detection limit. Here you see the range 110, 1.1.01. Here you see the detection limit ICP-MS is very low, means this is very sensitive technique. Graphite furnace atomic absorption. Here you see this is the second one, and here you see the hydride generation atomic absorption is the least one, so it is the most sensitive one. ICP emission, here you see this is again restriction limit is from 0.01 to 10, and ICP emission radial is from 0.1 to 100, and flame is having the one which detection limit is not as compared to the other. It means flame atomic absorption spectroscopy is not that much sensitive as compared to hydride generation atomic absorption or ICP-OES. Analytical working range for the graphite furnace atomic absorption spectroscopy from 0 to 2, because these are relative. For the ICP, here you see from 0 to 8. For ICP-ES from 0 to 6, and for flame is from 0 to 4, and for the graphite furnace from 0 to 3. Okay, they are relative, means this is the highest one, this is the second highest, the third, and the fourth. Interferences in atomic spectroscopy, type of interference and method of compensation. In flame atomic absorption spectroscopy, type of interference is ionization interference, chemical interference, and physical interference. Ionization interference we can reduce with the help of ionization buffer. Chemical interference we can reduce with the help of releasing agent or nitrous oxide acetylene flame. Physical interference we can reduce with the help of dilution or matrix matching or method of additions. In graphite furnace atomic absorption spectroscopy, the type of interference is physical and chemical. Stabilized temperature platform furnace STPF condition should be stabilized. Molecular absorption, Zeeman or continuum source background correction should be done. Spectral Zeeman background correction. ICP emission, spectral and matrix. So background correction are the use of alternative analytical lines, internal standardization. ICP-MS, mass overlap or matrix, inter-element collection, use of the alternate mass value or higher mass resolution. Spectral interference, here you see this is for cadmium. Here you see the spectrum is 228.8 nanometer. For arsenic, here again you see the absorption is also at 228.812. Similarly for magnesium 285.213. For the iron is, so here you see there is interference effect. This we call spectral interference. Chemical interference, formation of a compound of low volatility. Decrease in calcium absorption is observed with increasing concentration of sulfate or phosphate. Here you see this is decrease in concentration when you increase the concentration of sulfate or phosphate. So the amount of the decrease in calcium absorption will happen. How to overcome? By increasing flame temperature, use of releasing agents, use of protecting agents. Performance criteria. Here you see cost, low voltage, moderate, highest and highest. Here you see for the flame atomic absorption spectroscopy, flame atomic emission spectroscopy, atomic fluorescence spectroscopy, ICP and XRF. Instrumental cost low in case of flame atomic absorption spectrometer. In case of flame atomic emission spectroscopy, low. In case of atomic fluorescence is high. ICP is high, very expensive. XRF is also very expensive. Maintenance is low. low, but in case of ICP is high and XRF is also high. Sample preparation is moderate, low, moderate and high. Speed slow, medium, fast, fast. Operator skill lower, moderate, higher, higher. So these are the performance criteria. Thank you.